introduce myself a little bit. I'm a self-learned civil data scientist and a lawyer in Taiwan. I'm a law school student, undergraduate from National Taiwan University. So if there's anything wrong with my presentation, I will be very happy to receive any comment. Today, I would like to share how to use error backpropagation to initiate deductive reasoning in deep neural network. First, I would like to talk about motivation, and then the technical details and applications, related works, and pros and cons, and future and ongoing works. First is the motivation behind our research. Our motivation is very simple. That is to mimic human deductive reasoning. But before we start, we'd like to talk about what is deductive reasoning and why it matters in our everyday life. First, we would like to differentiate inductive and deductive reasoning. Inductive, deductive. Simply put, you can think of inductive reasoning as a for function which maps state, action into future reward. We use this inductive reasoning every day. For example, we learn the results from our actions in different situations every day. After learning the consequences of our actions, then we can infer what we should do in the present situation in order to gain what we want in the future. And this is where the deductive reasoning comes to play. So as you can see, deductive reasoning usually comes after inductive reasoning. So you can see these two kinds of reasoning, in fact, took place in our everyday life and in our brain in every moment. As we all know, deep learning is very successful in modeling human inductive reasoning. But is there a way to model human consecutive deductive reasoning as we mentioned in the previous slide? This is the question we try to answer. Since deep learning is so successful, and deductive reasoning usually comes after inductive reasoning. So to model human deductive reasoning, we decided to exploit deep learning trained deep neural networks. Our very primitive idea is to exploit a trained deep neural network, which learns the state, action, and the future reward. Then, by this trained neural network, for a given state and desired reward, we update the actions by forfeiting and error backpropagation with the neural weights fixed. We hope that the neural network will then generate a good action. This process might seem very familiar to some of you. It's very much like deep dream. But however, things doesn't always go well as we expected. The question is why? After a few investigation, we found the main reason behind this failure is that when the actions being optimized under the neural network, the actions are factually performing gradient descent upon the error surface created by this single deep neural network. This issue is better illustrated when the state and action are only one vector. We can see from this left picture that with fixed state, when the state is fixed, the actions, in fact, is performing gradient descent upon these error servers, and there inevitably will be local minimum. So how to solve this local minima issue is we are going to talk about how we solve it. Our idea is very simple. If a single deep neural network is not enough, why not make it 2 or more, and randomly select a deep neural network for action to be optimized upon. It's very similar to stochastic gradient descent, but this time it is the trained deep network to be the stochastic object. Why it should work and why it should work. An intuitive explanation is that this neural network's ensemble method is analogous to traditional stochastic gradient descent. You can recall that in traditional stochastic gradient descent method, in each learning iteration, we randomly select a pair and input and output data for deep neural network to update its weights. So the error service behind this scene is in fact changing in each learning iteration. So the updated weight matrix in deep neural network can escape undesirable local minima. However, this time it is the trained weight matrix to be randomly selected. So the series of actions can escape local minima more easily. To differentiate our method from traditional SGD, we named it multi-weight matrix stochastic gradient descent or simply NWN SGD. Now we like to talk about the technical details. For your convenience, our method can be divided into 2 phases. First is the learning phase, and then the deducing phase. In the learning phase, we have deep network stochastically learn state, actions, and corresponding reward from digital environment by deep learning. And then we save multiple parallelly trained deep neural networks and their corresponding optimal rewards. So this is the deep learning neural network ensemble, and this is their respective corresponding optimal reward. Then in the deducing phase, given state, in each iteration, a random pair of optimal reward and trained neural network is selected, and then the estimated actions will be updated by forfeiting and error backpropagation. So in each update process or deducing iteration, a new or a random pair of optimal reward and their respective learned weight matrix will be selected for actions to be updated. So the estimated action can escape local minimum. After the update, we then decide the present optimal action based on time zero for the estimated action for the present given state X. For your convenience, this is the pseudocode for your convenience. As we can see, roughly the red box is the core of SGD. And then is the deduction phase. Roughly, the red box is the core of NWN-SGD. The above technical can be think of or imagined as having trained network serve as overall environmental perceptions. And by these experiences or given or desired optimal rewards, the neural nets figure out a present optimal action. In this sense, not only data but also environment perceptions are compressed into deep neural networks as experiences in the learning phase, allowing the deep neural networks as well as the experiences to be transferred or stacked as integrated object in the deducing phase. There are some benefits of using NWN-SGD. First, it helps input data or estimate actions to escape local minima created by a single deep neural network. Second, it helps generated or updated estimated actions to cohere to several kinds of optimal rewards. If there are several kinds of rewarding criteria or methods given to neural networks. Third, if parallel chain NWSGD helps access to optimal reward to tackle sparse reward problem. However, this method has its limit. We still need incremental learning process that allows neural network to discover paths to optimal reward. However, we'll leave it to future and ongoing works. We'll explain later. And then we would like to introduce a very important and extremely useful technique to significantly boost NWSGD. That is dropout by Srivastava. Sorry if I didn't pronounce it right. In each neuron in the hidden layers has the same probability to be dropped for each iteration in the learning, as well as the deducing phase for each set of weight matrices. Because dropout, in fact, trains a neural network ensemble in each learning iteration. So dropout implicitly increases the size of the trained set of weight matrices. As a result, the assistant actions can escape local minima more easily. We apply our method to different applications. First, we apply our method to traditional temporal planning problems, such as classic control. As we can see, as the size of the sets of matrix goes even bigger, the score goes even higher. However, in mountain car application, or in this pendulum application, we can see if the size of weight matrix goes even bigger, there's a little downward for the score. And then we apply our method to traditional adversarial planning, such as tic-tac-toe game. In this scenario, the deep neural network first learns the actions of player A and the B and the result of the gameplay. And then by these trained deep neural networks ensemble, the actions of player A and the player B are updated under the selected neural network with different target value, offset value. And then after the update, player A takes action and goes on to the next state of the game board. As we can see, this is some interesting phenomena created by machine itself playing with itself. It shows some kind of a certain intelligence. Then we apply our method to traditional spatial planning problems such as Sudoku. In this kind of scenario, the neural network first learns the rule in Sudoku. If the numbers are all different, then it gets reward. If the numbers have overlap numbers, then it didn't get any reward. After learning, then we feed the row and the column and the grid of the Sudoku table into this scenario and select a deep neural network for this row and column and grid to update its missing number. So each missing number will receive 3 gradients landing from row, column, and grid. After update, any missing number with highest value will be selected as the next visible number, and this process starts all over again until the next visible number is found, and there is no more missing number. As we can see, this is the result of part of our gameplay. It solves blank Sudoku. This is the result compared to other works solving Sudoku. As we can see, if the number of set of weight matrices is only 1, the accuracy is approximately only 50%. However, if the number of the sets of matrices goes even bigger, for example, 20, the accuracy goes to even higher, 97. Lastly, we apply our method to some interesting areas, such as explainable AI. First, we train multiple deep networks by traditional NNIST dataset. Then, by this trained deep neural network ensemble, an initiated image will be updated in each iteration with randomly selected trained deep neural network. After update, the image will present a salient image of the original input data on the corresponding category, namely C, acute. As we can see, as the number of settled matrices goes even higher, the updated image will be more salient under the corresponding category. For example, this is number 0, and when this number of settled matrices goes even higher for the initial image to be updated, the picture will be more salient. Now we would like to talk about related works. First is deep learning. The similarity with our model is very low because deep deducing requires no Bellman function. The learning phase in the deep deducing in fact replace Bellman function by deep learning's innate universal approximation ability. Second is the generative adversarial nets. It has a higher similarity with our model. However, deep learning generates patterns by using NWSGD rather than bottom neural network. Also, deep learning uses only data to initiate minimax scan. For example, as in the application in tic-tac-toe, we split the data of player A action and player B's action. Then we train their action respectively according to a minimax scan. So deep deducing uses only data to initiate minimax scan rather than bottom neural network. Third, differential planning, gradient explanation techniques, and the deep dream. These works are probably the most similar work to deep deducing. However, these works rely on a single deep neural network, and they think inside deep neural box. We propose NWNSGD and show that this works in fact point to one direction, which is the potential deductive reasoning ability in deep neural network. Now we discuss the pros and cons concerning deep deducing. The pros is first is since biological. Since the brain neural has many pathways from later layers back to earlier layers, so it's possible we update our actions in our brain this way. Second, it needs no expert design function such as Bellman function. Now we discuss the cons concerning deep deducing. First, it still needs digital environment. Second, it requires a very heavy parallel training in the learning phase. Third, and this is probably the most important cons in our present work. That is, this is sometimes impossible to generate actions with corresponding optimal reward, unless we manually give some human X behavior samples, which is behavior learning. But as we all know, there are many areas where the cost of human expert is high, or there's no even human expert exist. For example, nuclear fusion control, wind turbine use system control to avoid Wakers effect. So we still need incremental learning process that allows neural networks to discover paths to optimal reward. We will leave this to future and ongoing works. The authors, how are we going to do? The author primitive idea is to refine the learning phase. In this kind of refined learning phase, the neural network does not learn from environment stochastically, but rather it learns by its deduced result to initiate a process of incremental learning by deducing, to let neural network itself to adapt itself to the environment, allowing neural network to discover path to optimal reward by incremental learning process. The deducing phase remains the same. This is the pseudocode for the refined learning phase. As we can see, in this scenario, the neural network does not learn from the environment stochastically. Rather, it learns from the environment incrementally. First, the neural network arrives at deeper state as time increases. In order to let neural network learn from environment incrementally by the deduced result. Second, as the deep network arrives at deeper state, in order to go even deeper, the neural network has to change its target reward and initiate the deductive reasoning. And then by its deductive result, the neural network learns the reward and the deductive result and the state. And by this iteration, as in the next iteration, in the next epoch, a deeper state will be reached, and the neural network will start to explore the environment even further. However, this scenario has one pitfall. As we can see, as time t goes by, the time required to deduce to certain deeper state will be even longer. And in each learning, as a result, in each learning iteration, the learning time will be even longer. So this is some problems we need to tackle in the future. But thank you for your attention. However, this work is in fact a one-man team, so the author will be glad to be part of one. Thank you. Thank you very much.